So you can actually defer all the way up to the numbers. And there's usually a sign bonus which can help you cover.
Okay, so today we'll be talking about interaction. And it's going to be a lecture with like a fair number of videos and so on, so this should be fun. But first I want to talk a little bit about projects. So it's about time to start thinking a little bit about your project. It's not like the first stage of the project is to announce your project title and your team by October 19th, so this is like about a month from now. But it's time to start thinking about what you want to do and who you want to work with. Your project proposal, where you need to figure out the details, are due on October 26th. And so I would recommend that you use fall break to think about this and get started on your proposal. Notice that the proposal is due at the same time as homework 6 will be. And if you have questions about the scope of your project or what your project could be or what are good ideas, I would recommend that you come to my office hours and talk to me about that. So the things that you need immediately is, or more or less soonish, is a team first. And so we have a Slack channel that's called Looking for Team Members that you can use if you don't have a team already. We're looking at teams of 2 to 3. We sometimes make exception for like single person projects that has to have like good reasons. Things like, hey, I'm a PhD student, I work with this confidential data that I can't share with anybody, can I still do a visualization project in that? That would be like a good reason for that. And we very rarely, but sometimes allow 4 per people projects. But essentially shoot for 2 or 3. And then I think the most important thing is that you, before you commit to a project, you should figure out your data. And I say this because whenever I've seen projects go wrong, it was like most likely because the data wasn't available. So for example, you have an idea of where you can get the data from, but you should also figure out that you can really get it. So once I supervised a project, still as a TA a couple of years ago, and they tried to get court decisions from PDF documents. And it turned out that parsing PDF documents was so hard and so time-consuming that they never got to the interesting parts of the project, and they had to switch projects completely 2 weeks before the deadline. And so just make sure that you don't get into this situation. There is a lot of text about projects and what are the expectations on the website in the project section, so it's not a good time to really read this in detail. And of course, you also need an idea. What do you want to visualize? What is it that you want to ask? What kinds of questions? The stages here is, there's 4 stages to your project. There's like the announcement, which gives us time to check and to assign TAs to your teams. You will be working with one TA in like a close collaboration to get this project as good as possible. Then your proposal, which is 5% of your overall grade. Then your project milestone, which is 10% of your overall grade. So just your milestone one milestone has as much value as 1 exam, right? So just make sure that overall the project is 40%, which is like the majority of your grade. So homeworks altogether are also only 40%. And then we have 20% for exams. And then your final project includes a couple of components. Not only the implemented visualization, but also like a process book where you discuss your design alternatives, your progress, how you implemented things, where you document something. And there are some examples on the website about that. And then we also ask you to create a 2-minute narrated video where you screen record and talk while you demonstrate your tool. And I would also recommend that you put some effort into this, because this is what we are using, at least what we primarily use to judge your projects when we look for best projects. Your TAs then will look at your project in more detail, but we have one long meeting where we look at all of those videos to pick out the best projects of the bunch. And then your visualization should also be live on the website, on the internet. And there's also instructions on how to do this. We recommend that you do it with GitHub Pages, and we recommend that you make sure that this is available long term. For example, if you host it via GitHub Pages, it doesn't cost you anything, and you don't have to pay for let's say an Amazon Web Server or something like that. We do make, this is not mandatory. There are some good reasons to not do that because, like, for example, confidential data, but in that case, you should talk to us. So by default, if we don't make an exception, we do expect those things. In terms of projects, I would encourage you to think about things where you shouldn't build like, here's 15 data sets, you can now explore them. You should try to tell a story about your data. Take the New York Times examples as like a guideline. They have like annotations, they give you different states, they do highlights and so on. And so we'll talk more about how to do these narrations with visualization tools in the future. The requirements is the scope. Like, you should be a bit ambitious with your scope, and basically after your project proposal and even before that, by meeting with me or your TA, you will be agreeing on a scope with your TA. And then you should think about your goals and categorize them. Like, you should be ambitious in your goals, but it's also okay not to be able to get to everything, right? So you should, in your proposal, should kind of classify immediately, these are the things that we really need, these are things that would be nice if we actually can manage it, and so on. You can also check out on the website, we have a category, like a page, that's the Hall of Fame, which are like the best projects from a couple of previous years. The minimum is like an original idea of a dataset and visualization combo. So you can't do like the parse dataset and visualize it in parallel coordinates, because that has been done many, many times before, right? You can find the code for that on the internet. You need to do something new, and it doesn't have to be like new in terms of research, but just something creative. It needs also to be interactive, and we also ask you to use at least 2 coordinated views. Like in this homework, for example, you have a map and a scatter plot, and coordination between those two, and that's kind of like our minimum requirement. There are exceptions. For example, if you build like a super intricate and very powerful single view, that's okay too. But generally, we would like to see 2 coordinated views. And so, I also want to just show 1 or 2 of the Hall of Famers from last year. So, this one looks simple at a first glance. It's basically on-time performance of the United States, and if you click on, let's say, here Salt Lake City International Airport, you see where they fly to, and then you see like what the delays cause. But it has like a lot of additional information about all of these charts here. So and that is quite like well synchronized. It updates in many different ways, and so here we have also like a connectivity chart. So this is a good project. What I do actually recommend to you, like, okay, so this is like also a really nice one. This is extremely custom. This actually works with the Spotify API. It's like an exploration of, let's say, rap and hip hop music, and it has a couple of different dimensions. So you can like hover over this, and like here you have rankings. You can look at genres, and then you can highlight where are these genres, and you can actually also play the songs right from your visualization. There's a little much here. So this actually uses the Spotify API. You can like highlight interactively. There is like different like visualizations that use either the album covers and so on. So that was a really well done visualization. And here is the like the second place winner. Which is what is really cool about this one, even though it also looks fairly simple on the first look. They have a time slider like we have in our homework, but it's not just a time slider, but notice that what happens to Russia here it suddenly changes to Soviet Union. So they actually have like different world maps for like, each of the years, and then you can like you get detailed views. You can like color them by things. I think by more recent data, you can zoom this whole thing, and then you can do comparisons and so on. So like play with those. Generally, I would also recommend that you don't like. There's a lot of stuff in the D3 galleries, and like we see fairly a high number of projects that just match up 2 or 3 of those visualizations. We would really encourage you to build your own thing, right? You don't have to like use somebody's code, but you can actually be quite creative in what you create. So like here is an example that is basically your homework 5, and that is an extremely custom visualization. Here we show a table of soccer results for the World Cup in Russia, and you can drill down interactively in this table, right? There's a couple of custom visual encoding, so there's not a single line of code that you will find like this on an example on the web. We're not for your projects. You're allowed to use code from somewhere else if you're explicit about it, right? But we also are not gonna like if you take 2 views from the internet and just hook them up to work together. That's not going to be a great project, and we might actually tell you ahead of time that this isn't really what we're looking for. So questions about the project. Yeah.
Where do we get our data?
That's you can on the internet is the there is a resource page on the website that links to a couple of data sources. You can get like data from the WHO. You can get data from the United Nations if you look at the global policy or something like that. You can get data from APIs. You can download Twitter data. You can get data from Spotify. So it's really like think about what is interesting to you and what would you like to do as a data exploration project, and then work on that. So, for example, just yesterday, the New York Times brought out like a pretty cool project where they showed how our friendships distributed across the country, right? And so they used some anonymized Facebook data for that. The one thing that I would recommend not to do is Kaggle, because like Kaggle is this like repository of data sets for machine learning, and those tend to be like overly like many people have used those before. And they also tend to be like slightly boring. So and like for example, many governments, city governments, state governments, and so on, make things available. You can look up, let's say, divorce records, court records of the state of Utah. You can get all of that. You can get like professor's salaries if you want to on there. Other questions? Okay. So then let's talk about interaction. Well, first, next week, I'll talk about actually about designing visualizations on Tuesday, and we will be reading this paper here for that. That's again one of those that is fair game on the test. And then on Thursday, I will actually be in DC, and so Sam will be lecturing about D3 layouts, which you will be using for homework 5. Any other questions about organizational things? Okay, so interaction. Why do we need interaction? Well, we have this spectrum of static content where we have like infographic in books to dynamic content. And by dynamic content, I also distinguish between animated content where we have essentially like basically autoplay that could be a video, but it could also be like animated with JavaScript. So the user is not in control, or truly interactive content where changes are the results of a user action. And so we mostly care about this truly interactive piece where the user steers what is going on. And so why do we actually want to interact with visualization? Because just looking at the complex data set, it's very often not sufficient to just look at one picture. You can answer a couple of questions with one picture, but you can't really fully explore a data set. There's usually too much data in a sufficiently large data set, and there are too many ways to show it. So remember this data visualization here that I showed for the corporate taxes on the New York Times. Here we had a couple of ways to interact, right? So we could actually hover over each of the nodes and get like a pretty good tooltip. So that is kind of like a piece of interaction, right? I can ask, what exactly does this do? And then I could instead split it up by industries. And now I have kind of faceted this view and I've done this interactively. Now instead of giving an overview of the whole market, I'm showing parts. I'm showing the tax rates for different sectors in the overall economy. And so this would be really hard to visualize all of this at the same time. And so therefore we need kind of interaction to reveal things like details on demand or to look at different perspectives in data. Interaction also amplifies cognition. We then tend to understand things better if we can touch them, right? So it's really important for us to play with something and if we can observe cause and effect. This is a tutorial that I will be coming back when we talk about data analysis and how we can integrate it with visualization. This is principal component analysis example. But here, this really is a way of understanding principal components, and by interacting with that, I can basically, here I'm changing the data. So this is my original data set, and here I get like the PCA, the first principal component and the second principal component. Of course, I'm mapping a 2D space to a 2D space, so that's not particularly useful. But generally, I can kind of see what are the results, what is the impact of moving something around, and I can immediately understand what is going on. And here's a 3D example of that, and I can also drag that stuff around to kind of interact with it. So by touching, it's not like physically touching, but it's very similar to physically touching. We can play with something and then we can understand cause and effect much better. So there's a lot of interaction methods. And I guess you, as a visualization designer, you have to ask yourself, what would you like to design for? Standard here is mouse and keyboard. That's kind of what we use in desktop computers, and which is still, at least for sophisticated visualization tools, that's still kind of the best way to interact with it, because it's you can you have very detailed pointing abilities with your mouse as opposed to touch or other modalities. You have a context menu, a right mouse click, and all of the things that you sometimes don't have. Touch interaction is an important modality, and especially I was designing for mobile interfaces, but I really want to talk about interaction. Gestures, do you think it would be interesting to use gestures to do data visualization? Can anybody come up with a scenario where you could use a gesture to navigate, for example? Eye movement is I'll talk about this in a second. But let's say I want Google Maps, open up Google Maps, right? And I could have a webcam, and I could just pan like this.
Yeah.
Is that a good idea necessarily? It might look weird if you're in an open office space, right? Yeah. So I'll show you a video about this in a second, and of course Tom Cruise here, Minority Report, the interface of the future, ? Eye movement is something that is a bit tricky. You can do things with eye movement, and you can, but it's mostly used for assistive technology. Actually, I wrote once a paper about using eye tracking to show details about the stuff that you're looking at. But what do you think is the problem with eye movement?
We move our eyes a little bit all the time to scan.
Exactly. Eye movement isn't really something very conscious, right? A selection or a hover with a mouse is something that I do very consciously, but I move my eyes just to look at stuff all over the place. And that's called the Midas touch problem, because everything Midas, the story of Midas is everything he touches turns to gold. And if you implement user interaction with eye movement or with gaze, then you have a problem of not being able to separate consciously looking at something and involuntarily looking at something. Speech is who has who does Amazon Echo, Siri, or Google Home here? couple of people. So I think this is getting kind of convenient. So for example, I prefer to set my alarm by speech because it's like 5 different buttons that I have to click on my cell phone. But for data visualization, it's still, I think like textual queries and reasoning about textual queries is an area that is quite interesting. But at least for now, it's kind of a niche area in data viz. So I want to show this video. It's like a 5-minute video about unconventional interaction models.
Hi, I'm Alex Kaufman. I'm an interaction researcher, which means that I explore and prototype future uses of technology as a way of understanding the future. And I really, really hate Tom Cruise. I specifically hate Minority Report Tom Cruise. With his perfect haircut and his power stance, chopping at the air to sort of scroll through scenes of crimes that haven't happened yet, because it has conditioned us to expect that the future of gesture interfaces is going to look dramatic. You know, all the gesture tech we're building, the leaps, the connects, the Mayos, they all demand these highly visible gestures that are distracting us from a more pedestrian, less cinematic future that is definitely more usable than this. I mean, every time I see this scene, I think, Tom, you're standing 2 feet away from the screen. Why don't you touch it? He's replaced direct manipulation, which our hands are really good at, with this kind of elaborate sign language, which our hands are really bad at. It's as if I said, like, it's the difference between solving a Rubik's Cube and explaining to somebody how to solve it by pointing. And the thing is, our hands are very coordinated. I mean, you can be walking down the street and pick up a penny without breaking your stride. But unless you're a mime or a dancer, you're going to have a really hard time pointing at the same spot in space twice in a row. And anybody who's ever used a Wiimote knows it's really hard to point precisely. But I think there's a feeling among people that somehow getting rid of a controller makes an interaction feel more natural. And people become so obsessed with this idea of getting rid of the mouse and replacing it with gestures that they've actually forgotten how we use our hands. Because most of the time, we're not gesturing. In fact, 90% of gestures occur when we're speaking. And studies have shown that all of those gestures, almost to the last one, are for the benefit of the speaker. They help the speaker keep track of what he is saying. They convey no useful information to the audience. Now, I'm not saying that we can't use gestures and interfaces. What I'm saying is that we've got to pay attention to what their unique characteristics are. They are fast, they're silent, they can be performed at sort of any variety of distances, and most importantly, they have this kind of inherent directionality. So at least in theory, you could use gestures as this kind of meta-unifying input across a series of devices. And what I mean by this is, for instance, if I point at my stereo and it turns on, and then I point at it and it turns off, and then I point at my TV and it turns on, and I point at my TV and it turns off, I've actually established a common language that both of these devices understand. And I can use this language as a way to connect them in a very intuitive way. So, for instance, if I point at both my TV and my stereo, if the TV is on, it pipes the sound to the stereo. Or if the stereo is on, it actually pipes the music video of the song that was playing or the album art. This all sort of presumes that gestures are these explicit and very deliberate motions. And I think actually the real magic happens when the applications start to pay attention to what we do with our bodies normally, what we do with our hands normally. Because once machines can interpret our normal motions, they can find some insight into our intentions. And machines that understand intentions can actually start to help us. So for instance, if I'm sitting on my couch watching my TV, and I pick up my phone, maybe I'm one swipe away from the remote control app, or from the Netflix app. Now, if I happen to pick up my phone while I'm looking at my stereo, that same swipe might take me to my music playlist. Similarly, you can imagine a situation where picking up the car keys from the table as I'm walking outside takes the last 5 addresses that I've looked up and just sends them to the car's nav system, and grabs that podcast that I was halfway through, and sort of cues it all up on the car radio. And ultimately, I think that this is what the Minority Report interface is getting at. I don't think anybody, not even Tom Cruise, really wants a Dance Dance Revolution version of Photoshop. I think the goal here is it's really to help people to establish physical mastery over a digital world that's becoming increasingly complicated and hard to understand. And so I think that in order to be commercially viable, these gesture interfaces can't require us to learn a new abstract physical language. They're just going to have to learn to find meaning in the movements that we already make.
Yeah, I think that's an important point, especially the last thing he said. Finding meaning in the movements that we already make. That's like a big problem with all these kinds of like interfaces where you put in, let's say, a text query or a speech query or a gesture interface. What is the problem that I'm talking about here? How do you know what this tool can do for you, right? These interfaces, once you know them, they can actually be quite powerful, but they have a problem of discoverability. What are the features that are accessible? That's really tricky, and that's much easier to do if I have like a screen and I see all the buttons and the buttons are labeled, and then I can get an idea of what the buttons are about to do. There is like two essentially like main paradigms of like and interacting with interfaces. The one is direct manipulation, and the other one is indirect manipulation. So what's the distinction here? When I do direct manipulation, which is especially important in data visualization, I directly interact with the data. So for example, I have like here this scatter plot, and that's I can do like a rectangle selection here, and now I actually take this this rectangle selection and move it around, and I see that this is highlighting across all of the views. But here I have like defined something which is my rule of what I want to highlight, which is this rectangle, and I can touch this rectangle with my mouse, I can move it around, I can resize it, and so this is as direct as it gets, right? I'm really working in data space. As opposed to that, I could have like a list of sliders here on the side that say, for dimension sepal length, show me this range. For dimension sepal width, show me this range. And then I could like use the slider to interact with that. And that's indirect manipulation. I'm manipulating a widget that kind of has an indirect effect on a data visualization. But studies have shown that direct manipulation is easier to learn and much more powerful. And so it's not always possible to do direct manipulation, but you should always strive for doing it as direct as possible. So there's a couple of other ways of thinking about visualization. We have the different types of interaction. So we have single view interactions. For example, when we navigate change over time, when we so for example, we look like in our homework 4, where we have the slider to change time. That would be an example for that. Navigation would be like zooming and panning on Google Maps, for example. Semantic zooming is something that we'll be talking about a little bit later. Filtering and querying, and then focus and context. This is all defined on a single view. In visualization, another very important paradigm that we'll be talking about in a dedicated lecture is multiple views. So for example, in our scatter plot, we have, in our homework 4, we have a multiple view system, right? We have our map and we have our scatter plot. Those give us different pieces of information, and we need to connect them in some way. And so we can do that by doing linking and brushing in this particular example, or selection, or we can adapt representations if we do multiple views. There is going to be a dedicated lecture in our near future where we talk about these multiple views. So now I want to talk a little bit about this paper, the Interactive Dynamics for Visual Analysis. So anybody want to give a summary of what this paper is about? Yeah.
So they basically they describe different like attributes or things that good interactive visualizations should have, and gave a breakdown. So they put it in 3 major, they called it a taxonomy, I guess. Put it in 3 major categories: data view, specification, view manipulation, and process and provenance. And then for each one they had 4 like little subcategories where they described like different tools that are available or things that you should do, shouldn't do, and
Yeah.
that's pretty much it.
Cool, yeah. So this is kind of like a paper that is not necessarily a research paper, right? This is a kind of like written by researchers in the field for a general audience. So did you get that sense, like compared to the paper we read last time? Did that feel a little bit different? So you picked up on that. Okay, so let's look through those things. Like maybe like a question first: are all of these equally intuitive to you? Would you have thought about all of these when I say interaction? If not, which one was kind of like odd? Yeah.
I think guide and process was a bit odd because usually we just see a visualization and we think on our own.
Yes. So, anybody else? Yeah.
I actually thought the first one, visualize, I don't usually think as interactive because usually I think of someone choosing, oh, I'm going to represent this with a bar chart, and it's not something that I choose or interact with.
Yeah, yeah. That's also something that kind of like, I think it's useful to think about this way, but when I read this paper first, I also had like, this is interaction, yeah. But if you think about it, it actually is. If you like and the classical example here is Excel, right? How do you do this in Excel? Yeah.
You can like select the type of chart that it is, like a line chart, a bar chart, or whatever.
Exactly. So you first have to select which data range, right? And then you select which chart. What would be this operation by choosing visualize data by choosing visual? I think that is a little like, they explain this a little bit more, but in this, by choosing visual encodings, it's also about choosing data. What would be an example of that in homework 4? Exactly, the drop-down boxes, when we choose what we want to visually encode. Then filtering, filtering is kind of, I think, obvious. Sorting, like what is the benefit of sorting?
Better compare values. Search.
Yeah. So I can ask certain questions by sorting, right? Usually I can ask questions about the maxima of one dimension or the minima of one dimension. They also talk about a special kind of sorting. Anybody picked up on this? When I have like not one dimension but multiple dimensions, and I want to sort by that. It's called seriation. What does that do?
Kind of minimizing the distance measure between two attributes and accordingly.
Exactly. So we can come up with like a more advanced sorting interface would be to define a distance function over multiple dimensions in a data set, and then minimize and then sort by that distance function. So we'll see that, for example, when we talk about adjacency matrices for graph visualization. Do we do any organization of multiple, maybe derivation? Like, have we used any derivation so far in this class? Anybody can think of anything? The answer is like not really. What would you do? Like, what would be an example of doing this derivation?
Statistical data.
Yeah, you could use you could calculate the mean and represent the mean, for example, instead of all of the data points. Or let's say I have incomes and costs in a spreadsheet, and I want to plot my profit. What would I do? Yeah, I would create a new column, derive the data, I could put in a formula into my spreadsheet and say income minus cost. So this is what they mean by derivation. View manipulation includes selection. I think that's rather intuitive, so let's skip over that. Navigation, I think also fairly intuitive. What is view coordination?
Talked about it earlier today, but having multiple views coordinates such that when you change the slider or run a bubble, it impacts the coordinated view.
Exactly. We could also, in theory, like selection coordination, highlight coordination is one way of doing it, right? We could also do navigational coordination. For example, if let's say we look at an MRI scan and we have like a volume representation and we have a slider, we could kind of like click on one view and then the volume would automatically transition to show me that view parallel to the screen. So we can do like all kinds of things to synchronize multiple views. And the whole provenance and process, the whole provenance and process section here, I think is quite important, but especially in research papers, often overlooked. So what is provenance? Have you heard of like the provenance of art, like a painting?
It's like a realization.
It's it's not really. So provenance in art for paintings, for example, would be the history of it, who owned it. Like this is actually like for museums curators, a big deal is to investigate the provenance of like artwork, especially to see whether it like hasn't gone through some illegal channels or wasn't kind of like disowned in like Nazi Germany or something like that. That's a common thing in art. And so for what could that be for like interacting with visualization? What could provenance here be? Yeah.
To make sure that you are not manipulating the data so much that it is no longer honest to what the underlying data is.
That's part of it, but there's a simpler
Source. Like revision.
a revision history. What would you say?
The source.
The source of the data is an important part of that, yeah. But the simplest part is simply your undo redo stack, right? So that you can basically undo operations that you did. That's like, and not necessarily just a simple undo redo stack, but kind of logging and tracing all of the steps that you've done. And then, so that's kind of important because very often, especially if you're new to an interface, you kind of want to be able to undo. And sometimes operations in visualization systems are not that easy to like undo unless you have an explicit undo button. Annotation is something that is very important, and that's also something that I would really recommend for your project, as I mentioned before. We don't want just like very often there's like the exploration phase where I look at the data, but then if I want to communicate this to somebody else, I might want to annotate it. I kind of like want to capture my findings. What did I see? What are the things that are especially worth paying attention to? And so that's where annotation comes in. And then share views and annotations to enable collaboration. I guess the holy grail of most visualization systems would be something like Google Docs for visualization systems, right? Where you can simply say, hey, give people access to my visualization. They can like look at the whole history of what I've changed. They can continue working on it for you, can like leave comments and so on. So this is also an important piece. And then guidance, I think, is kind of like the hard piece, and I think the most researchy one, where you kind of like analyze what people did in the past and then maybe make suggestions and like, hey, you've done this, maybe like one sensible solution for you to do next would be that. But I think this is like, there's very little practical interfaces that already do that. Okay, so now let's like look at this one by one. If you want to look at change over time and transitions. So change over time is like easy to represent with a slider to see or view the data at different times. Basically what we're doing in our homework. Here is a visualization that was actually a visualization project from a couple of years ago, where you see how the railroads changed America. So you have like in the background the map of America as it is now, and then you start to see kind of missing the black things here are the railroad lines. And then you see that railroads are starting to be built, and now we have like the connection, east-west connection, which then is followed quickly by more and more states joining the union. So that's like an example of using a slider in a little bit of a different context as we have it in our homework. But sometimes it's better to show these differences explicitly, right? We talked about this last time, that having these animations, whether they're based on a slider or automatic, it can be tricky to keep track of changes. Sometimes it's just better to, instead of showing that using interaction to do that, to explicitly encode the change. And change over time doesn't really have to be literal time. It can also be things that change as you go as part of the analysis process. When I like manipulate something, like here I'm like changing some layout parameters for a ranking visualization. We also talked about transitions mostly when we were talking about D3 and how we can do these transitions. And so why do we want to do transitions? Because different representations support different tasks. For example, like a bar chart versus a stacked bar chart, they show me, the one shows me parts of the whole, the other one allows me to do better comparisons between the groups. So maybe that's something that I want to look at. Or I might want to change the order to sort. And then it kind of is helpful to have a transition to keep track of what is going on. So transitions are really about making it possible for users to track what is going on. So here's like an interesting example. I hope this still works. It's a couple of years old. No, it seems to be broken. Anyways, so this visualization here will transition between a couple of different ways of looking at it. Here we have a sort like a visualization where we can like, this is about set visualization, so we'll be talking more about this at some point. But let me just pick an interesting data set. But one way of interacting here would be, like here I have different sets of sizes, and then I can ask sorting questions, right? And here is actually, like if I sort by something, we have an animation that kind of like gives us an idea of how things are moving around. Like here we have an example of like a detail zoom, like basically that's something pretty sophisticated. You're looking at the radial visualization of a hierarchy. We'll talk more about these kinds of plots when we talk about tree visualization. But essentially what we're doing here is we're clicking on one segment and then want to look at the detail of that. And the animation here shows us what exactly is being zoomed in. So here we have like a very sophisticated animation that first goes out of this larger segment and then expands to use the whole space. Up here we have a transition between stack to group bars. And so you can actually switch here, and that's also quite well done, right? So you know exactly what is where. So do you think that animation is always a good idea? Like animated transition? So sometimes it's like, especially if you have too many things happening, then it can be detrimental. But so here's like a nice video.
When analyzing or presenting information using statistical data graphics, it is common to look at a number of related graphs. For example, the viewer of a bar chart may want to switch to a pie chart to view relative percentages, transition to a scatter plot to look for correlations between two variables, or drill down by breaking up the data by categories. Animation is one promising approach for facilitating perception of changes when transitioning between data graphics. Using design guidelines motivated by research of human perception, we have developed Dynaviz, a system supporting animated transitions for statistical data graphics. Dynaviz provides animations for a number of different transition types, including changes of perspective, filtering operations, and viewing changes of data over time. In some cases, changes of value require changing the axis scales. Here we show a sorting operation. Animating everything at once can result in items occluding each other. By slightly staggering the movement of each of the bars, Dynaviz makes the sort easier to follow. Here, a bar chart becomes a radial donut chart. By growing the wedges to take up the whole circle, we form a pie chart. We can also perform drill-down operations, breaking up the data further into distinct categories. We can then unstack the bars to view the same data as a grouped bar chart. Of course, we can always reverse the transitions to return to the view we started with. We might want to compare different variables in a scatter plot to look for correlations. Here, we keep the y-axis values as the same as the bar chart, but use the x-axis to show a new variable. Animation is also helpful for showing transformations to the data. Here we show applying a base 10 log transform to the data. Both data and axes smoothly animate to show the results of the transform. Visual encoding such as shape, color, and size could be used to visualize additional data dimensions. To evaluate the use of animation in data graphics, we ran 2 controlled experiments. The first...
So I don't want to get into this. But yeah, these are just like all the different ways that you can use animation. So the caveats are that changes can be hard to track. So for example, in the sorting example that I gave earlier, we actually found that once you animate stuff that is off screen, so if I had like a lot of set intersections here, let me show you this. So I could add a couple of other sets, and then this is getting bigger and bigger. And then if I start sorting, and I have elements that are coming in from off screen, it gets kind of like not particularly useful anymore. So here, at some point, if this gets too much, we simply stop the animation, because if we don't see the origin and the destination of elements anymore because they're off screen, it really becomes quite useless. So that's clearly a point where you should stop animating. But even generally, it can be hard to track if you have too many elements. One approach that they mentioned in the video is to stagger animations so that you move only one element at a time, but even that breaks down eventually. And then the other caveat is that the example that we had with the fertility rate, US versus Japan, is this eyes over memory approach. So maybe showing different states in multiple views and synchronizing them might be an alternative to animation. So now I want to talk a bit about navigation. So like navigation, at least in 2D, we have pan and zoom, which are the most important animations. So pan is moving around that plane, and zooming is enlarging or making something smaller. Or if you like think about it from a computer graphics perspective, to move the camera of your scene. And then if you have like a 3D object, you can also rotate. And so here are 2 examples. Google Maps, the familiar one, the University of Utah, but I'm actually looking at it like here, I'm like panning or rotating in this case actually, and I'm zooming at the same time. And here I might actually call this like panning now at this scale, and I can keep zooming in. So this is like a very familiar interface that you all know. One maybe less familiar one is if you look at things like scientific data. Here we have an MRI scan plus some like pathways, some neural pathways. Hope it loads. Let's try it again. It loaded earlier. Oh well. Maybe my internet isn't fast enough here to load this quickly. Okay, I'm not like you'll get the link when I put the slides online. This actually works And here you can like rotate, but also like navigate by zooming and panning in this 3D space. And these kind of like 3D navigation things are quite tricky to do with our 2D input devices. And so if you're like a professional CAD designer, for example, if you're like designing cars, you would use like what's called a space mouse, where you can do these rotations very intuitively. It's a little bit more tricky with conventional hardware. Another way of interacting is storytelling. You've probably seen this before. And storytelling is about telling an interactive story, and the only interaction here is scrolling. And that kind of simplifies things, especially on a mobile phone or a tablet where you don't usually have precise interaction. You should, there's a couple of things that you have to be mindful of. So do you do continuous scrolling versus discrete states? Do you provide direct access to later states? And something like that you see, especially in early storytelling things, is that you do something unexpected that doesn't really fit the mental model of people that use storytelling. So I want to show you two storytelling examples. Here we have one from the New York Times, how the US and OPEC, this oil cartel, drive oil prices. And so I start just by navigating down in this chart. And then I see here oil supply versus prices. Like here on the x-axis we have the worldwide oil production, and then on the y-axis we have the oil price. And we see like there we have like the temporal data and these two dimensions. The temporal data is encoded by labels, and the sequence is encoded by these arrows. And so then we can like storytell, and it breaks it up into month. First, like we also like have the story here disappearing. It breaks it up into month, and then it changes it changes axis here. Now we're only looking at the OPEC production and so on. So here, I would say this is kind of like a little bit tricky already, because we have a quite significant change, transition here between like worldwide oil production and the OPEC oil production. So we changed the scale a lot. But it actually takes a couple of times and looking very consciously at that to keep track of this change, because it's very subtle that this axis suddenly changed from world to OPEC only. It's quite subtle. So here, I think it's terribly done, but it's maybe not the best example. I think this one here is actually quite well done. So this is what's warming the world from Bloomberg. And so here we see like a temperature curve. And then we can scroll, and then we can see, is it maybe the Earth orbit that is changing? And this is simulation data of where the temperatures would fall if this were, if we had these, if we made these observations, like what we would expect based on the orbital change in this case for the world. And we have like a band here for uncertainty. So this doesn't look like it correlates, and then you keep scrolling, and then you add in other things like, is it changes in the sun? Is it volcanoes? And we see some dips because of volcanoes, but it's not like an increasing trend. And is all three things combined? And so we keep scrolling like this until we get to more and more of these examples. And so I think this storytelling example does a couple of things right. So first, it doesn't do any subtle changes, right? Everything that you change is quite obvious. And then it also has this like state tracker here. So if you jump to any of those states, you have a good idea of what is going on and where you are in the story. And it keeps like the main, like you don't get disoriented. The changes are quite explicit, and it's easy to keep track of what has happened. Semantic zooming. Who's heard of semantic zooming? What does it do?
We talked about it last lecture in Google Maps, where there's like discrete places that Google Maps is zooming to instead of this continuous. It's like changing the data at the rotate.
Exactly. So one example would be that as you zoom in on Google Maps, you get additional labels. You suddenly have buildings appear and so on. That's an example of semantic zooming, but it could be more abstract. And so actually Windows 10 implements semantic zooming for their navigation menu. Like this is what this video is about.
Hello, my name is Adam Barlow. I'm a program manager on the Windows Developer Experience team. Today, I would like to introduce you to the semantic zoom control, which is included as part of the Windows library for JavaScript. Semantic zoom is a control used by apps in Windows 8 for displaying large sets of content in a truly user-friendly format. Semantic zoom is unique in that it provides an easy-to-navigate, touch-optimized view of the data you present to users. In designing Windows 8, we wanted to ensure users wouldn't have to pan tediously through large sets of content with touch. Semantic zoom is our solution to this problem. It gives users the capability of quickly jumping to sections of the view and greatly reduces some of the pain points traditionally associated with large collections. As you can see here, semantic zoom allows the user to quickly jump to any given location in the view, in this case, the last group of my start screen. Not only is semantic zoom a great navigation mechanism, but it also allows you to communicate a higher level of organization to your data, using the zoomed out or semantic view. For example, in the People app, you can zoom out. Here you will see a higher level abstraction of the data in terms of letters of the alphabet. This is extremely powerful and can be used to communicate important information to the users of your application. For instance, you could use the cell spanning functionality of the WinJS list view to demonstrate the relative sizes of your groups. Although semantic zoom is easily performed with touch using the pinch and stretch gestures, it also works well.
So the point about this here is semantic zoom, like in Google Maps, the example that we had earlier, is very natural, right? But because we simply add more detail as space becomes available. But we can also completely change the representation as we zoom in. For example, from an A that represents everybody with A, whose name starts with A, to detailed who are the people whose names start with A. Here's another example. This is a research paper.
LiveRack, interactive visual exploration of system management time series data.
So here, what they do is they look at performance data from like some compute center, and you have like a high-level encoding with red, green, and blue. But then you can actually zoom in and select one region, and this is like right now you're looking at the state, right? This is what it currently looks like. But once you zoom in, or once you select one dimension, then you will also get temporal information about this particular, let's say, how much like network traffic do you have or something like that. So here you can see that they increase the size, now new details appear, and now we actually, is that we have reached like a resolution that is sensible, we get those little line charts embedded here. So we've kind of like zoomed in, and like now that we've zoomed in more, we see labels on these axes. Before it was just sparkline without labels. Yeah, and so like basically what you have to do if you build a semantic zooming interface, you have to really think about what do you present at which level of detail. And that's tricky sometimes, but it can also be like a quite powerful approach. So the next interaction paradigm that I want to talk about is focus and context. So focus and context is really about carefully picking what to show in detail and hinting at what you're not showing. It's basically a synthesis of visual encoding and interaction, where some person interacting with an interface selects a region of interest, which is the focus, either through navigation or selection, and then we provide context through aggregation, reduction, or layering. So this is like a very high-level description, but it will be more clear what I mean. And so there's 3 different ways of doing this: elision, superimposition, and distortion. And elision is essentially like this, showing details on demand. Superimposition is like showing things on top of each other. And distortion is giving us like more information or more space to something central at the cost of something else by distorting our viewing plane. Elision is, for the non-native speakers, like in general English, it's the omission of a sound or a syllable when speaking. So like I am would be I'm, or it's instead of it is. Here it really means that we show a focus item in detail and other items are summarized for context. This is an example for that. So we have, this is the space tree, and we get some like context about this larger tree, and we get these indications that there is more by looking at these triangles to the right, but only when we click on something, we reveal the details about what is actually contained in the data. A quite important concept here, especially historically important, is degree of interest. And degree of interest is defined based on two terms. If I have a data set, I can define for every item how interesting it is. And I use two terms for that. It's a priori interest, like how important is this element in the first place, and the distance from where I'm currently looking at. And the degree of interest, at least according to this definition by Furness, is this term that combines the two, this a priori interest and the distance. And so the idea here is that you want to look, globally, you want to get an overview of all the very important items, but in your neighborhood, you want to get more information about things that are close by. So think about navigating a large tree, let's say a tree of life, a phylogeny. If you look at a specific species, you care maybe about where does it fit into the larger tree of life, and you maybe care about its immediate neighbors. But doing that and how you define what is interesting is what you do with this degree of interest. So you try to find a global balance between local detail and a global context. And so here is an example of this DOI tree, basically what I just talked about. So here you have a measure of how important something is globally, and those are kept here at the top. And then depending on where I click, more detail is revealed automatically. You can also see this a lot in this in hyperbolic trees. Well, they are actually mostly local. So my caveat here, that's from personal experience, is the distance function can be sometimes quite tricky. So if you work with these DOI trees, for example, and it doesn't only apply to trees, it applies to anything. What you do if you click somewhere is you reveal information, and that kind of can be quite involuntarily. And so I personally prefer to use this DOI mostly with a priori interest, and then let people explicitly specify what they are interested in, instead of using this distance function in addition to that. Yeah?
Does it have anything to do with the knowledge tree of Google? That is you look for something and it shows you a little history about the concept.
I don't know the knowledge tree of Google, so so I don't really know.
Yeah, it's a little the most important facts about some person you're looking for.
Yes, it sounds feasible, but I don't know this example. But yeah, the idea really is that, for example, in a tree or even in a document, let's say you want to use a DOI approach to text, to a book. You would get the page that you're looking at, the sections that were immediately prior or after your current chapter, and then you might get chapter headings for the rest of the book. That would be an example for a DOI function for non-tree data. Superimposition is when a focus layer is limited to a local region of a view instead of stretching across the entire view. So what do I mean by that? That is essentially this idea of magic lenses. Who's heard of magic lenses before? Okay, do you want to summarize what they are?
Isn't that a stage that will perform
Exactly. So you kind of have a lens, and you can use the lens to learn more about an area. And I'm not talking about the geometric lens here, but about the magic lens. It shows us things that are different. So here, this is a paper from 1993.
Blue glass sheets can include magic lenses, visual filters that modify the appearance of the objects beneath them.
So this is a geometric
For
lens.
example, this lens magnifies the objects underneath. We control the magnification with this slider, increasing or decreasing. This second lens is a filter that shows only red objects. Overlapping the two filters composes their effects. When we place the magnifier lens over the red object lens, we see that this little red object is a Time magazine.
So I would actually more specifically call just this filter the magic lens. The other one is just a regular lens. But here you have some smart way of filtering out only red objects. But that could be also something different. So here, for example, is an example. Here's one example where you can look at actually a physical lens that, like, you use a physical sheet of paper and some smart projector setup to show different aspects about the human anatomy.
The user interface and software engineering group at the University of Magdeburg, Germany, is demonstrating a set of novel navigation techniques for exploring information spaces by using tangible magic lenses in a tabletop environment. Up to now, tabletop interactions are limited to the two-dimensional surface. In this example, users can zoom and pan through large pictures by performing multi-touch gestures on the table surface. In the following, we show how this task can be accomplished in a more natural way. For this purpose, we developed a paper-based mobile display that users can freely move through the physical space above the tabletop. This magic lens works as a magnifying glass to zoom in on an image by simply lifting or lowering the lens. At the same time, moving the display horizontally results in a panning operation. In order to help users maintaining the context or data, with each data layer representing a unique feature, the layered information space is a set of two-dimensional data, with each data layer representing a unique feature of a contextual model. In our example, medical students can study different systems of the human body.
So yeah, so here we see what the magic lens does, right? Like in this particular example, and that the physical setup here isn't that important, but we have like a lens that shows us either the nervous system or the muscle system or the skeletal system, depending on which kind of lens I'm choosing. Anybody want to speculate how they implemented this with the tabletop? Yeah.
Maybe like shadowing and trying to find the center of that shadow.
That could be one approach. Anybody else have an idea? Yeah.
You might have a projector over it, and they probably do some kind of pattern recognition or object detection to just find the location of the square and just project the pixels.
Yeah, that's exactly how they do it. So they have like a table here that is like illuminated from the back. So the image here comes from the back, as in like most tabletop displays. And in addition to that, they have a projector. And when you put in a sheet of paper, they project on that paper, but only on this tiny segment of the paper. And so they track how this paper is moved about with cameras and then project only at that space. So that's a pretty brittle setup, but it does work. But it mostly works in these like academic labs, and once you like move the table a little bit, you have to recalibrate and so on. So it's a tricky setup to do. Another thing to do, like if you think about it, like a tooltip is actually a magic lens by that definition, right? Just showing a tooltip is a magic lens, and there's like, here's an example of a tooltip lens where you have multiple items in a scatter plot, and you would automatically have arranged tooltips around that lens. So the third thing here is distortion. And distortion is kind of like the classic focus and context techniques, where we use geometric distortion so that we see something in focus and give some context about the rest. Here is a pretty cool example of that. There's a demo. I'm looking at the evolution of movie genres, and I can pick an area that I'm interested in, and then kind of you see that this is distorted. So here, for example, I'm looking at like the middle of the 90s, and you see that punk was big in the middle of the 90s, heavy metal to some degree, and we saw that hard rock was probably more popular. If we can click that, we can see if we go back in time, we can see like hard rock being more important. Well, not much actually, but punk being like a major. Like, this is the number of bands, and so what we're using here for distortion is we use the linear distortion for for the years to really zoom in to see some more detailed inflections. And so we have multiple ways. We can actually have a fine-grained selection of how we actually want to do this transition, and so on. So that's like a decently well done example of geometric distortion. Another example here would be the perspective wall, which I'm mostly mentioning for like historic purposes. This is like one of the seminal papers from Xerox PARC. And
the perspective wall is used to lay out 2D information onto a 3D segmented wall. The front segment is used for viewing details, and the side segments provide context. In this case, each node represents a file with its horizontal position determined by its date of last modification. Vertical position is used to indicate the class of the file. When a node is selected, the wall moves to bring the selected node to the center of the front section. As before, we have a fisheye view. We're using 3D to make better use of available screen space, and we use interactive animation to exploit.
So this is paper from '91, so there was enough time since then to actually implement this in your desktop browsers. Why don't you think, do you have an interface like this when you look at your files nowadays? Yeah, so like the point here is that like you have this perspective distortion, and you see, like for example, if you look at temporal data, you could get an idea of what has been before and what has been afterwards. But like we'll talk a little bit more about disadvantages with distortion, but they kind of make it really hard to read the distorted segments. More generally, you can do these like fisheye lenses that kind of simulate a magnified lens. This can be taken to the extreme. Like here I'm looking at a hyperbolic browser. And the idea of hyperbolic browsers is that there's a version now available. The higher version. The idea of these magic lenses is that I have like, I click on a node and then we move this over as if it were to project it to, like, it's not a sphere, but it's a hyperbolic space, but think of it as a sphere, and I move over the sphere and I see more details about that browser. So that is kind of like a way of using distortion to focus in on what you're currently looking at and to navigate to other branches of the tree. So these techniques, they're like mathematically interesting, and I think that the hyperbolic browser here for the trees is also like pretty cool to use, but they really haven't caught on much in practice. Here's a more like another extreme example where there is a lens used to visualize a bus network in Singapore, and like this here is extreme with respect to the degree of distortion, right? So you see. Like one of the problems with these magic lenses is that you see something in detail here, but everything else here is squished to the side to some degree in some very unpredictable way. So it kind of can get tricky to find what. I should actually stop this because otherwise it's going to go all over the place. So it's kind of tricky to keep track of what is going on in the proximity. This is easier to do, like here as a simple demo. This is easier to do to keep track of things if we have not 2D space but 1D space. So here I'm looking at the ranking technique for universities, and this is like a long list of universities, and I can like click at something down here, and I can like navigate, and I get some sense of what is the data up here, and if I click on any of them, I will actually zoom in, and so I have this distortion effect. But it's not necessarily hard to navigate, right? If I click here, it's kind of predictable what is happening. So this is kind of useful in 1D space. It's a little bit more tricky in 2D space. So my concern with distortion is it's kind of like unsuitable for spatial judgment. So if you do something on a map, it's problematic. You have the overhead, the mental overhead of tracking distortion You have to visually communicate the distortion in some ways. Like you have to have like a radicule that deforms together with everything else, or some shading. You have the problem of target acquisition. How can I actually go to a place that I want to look? So you might lose track of that because of the distortion. The lens is displacing items. And so people have this was a big deal 15 years ago in visualization research. Where people actually ran perceptual studies and found that we are really not good at using them. It really it seems cool, but it is kind of tricky for people to use. And so the studies, there were mostly negative results. So nowadays, it's more like using 3D in visualization, right? There are scenarios where it makes sense and is justified, but very often you kind of want to not do it. Like a cool example of distortion is transmorgification. Who's a Calvin Hobbes reader? So, the transmorgification is when Calvin steps into his box and it comes out as a dinosaur or his character of interest. And basically, here the idea of this paper on transmorgification is to transform complex shapes in image space. And I really love this paper because it's so neatly done. So what they're doing here, they sketch a path, and then they linearize along that sketched path. And you can do things like, for example, compare the Mississippi River with the Colorado River in length by simply tracing it with your finger, and then plot them side by side. They also give examples for what you could do with an abstract visualization. Here you have an icicle plot, and you could do transmorgification, and this is all just on the image, right? They don't know anything about the geometry that's going on here. You say project this to a circle, and now I've made a sunburst plot out of the icicle plot. Here's a rose petal plot, and you could actually just take the image and by using this transmorgification, turn it into a bar chart. Okay, so I'll continue with the rest of this lecture next time. I think it's a good place to stop, and I'll see you guys on Tuesday. You can still register, but at this point, It's like if you're just not cheap, but it's like two. So there is next year in Vancouver, which is
not specified at the same time, I would say none of the scientific formulas should be together. I'm gonna double check that with if somebody uses the change theory to add a whole bunch of like I'm assuming like a warning rather than a that's what I think. They simply didn't go in and add in this case it was they did everything in three. They just didn't update the HTML by manually adding there they are updated the user change. Like it's fine. You could get possible and doing it that way, but but do it for